Tonight, we're going to explore 100 cosmic mysteries. Not all at once, not in a rush. We're going to let them unfold slowly, like stars appearing as dusk deepens into night. Some of these mysteries have names you might know. Others will be completely new. And here's the beautiful part. Each one reveals something strange, something we don't fully understand, something that makes the universe more wondrous than we ever imagined. Before we begin, if you enjoy these calm explorations of the cosmos, a quick like or subscribe would really help this channel. It's a small gesture, but it makes a real difference. Now, let's begin. Let's start gently with something that happened not so long ago. In October 2017, astronomers in Hawaii noticed something unusual moving through our solar system. They named it omuamua, which means a messenger from afar arriving first in Hawaiian. And that's exactly what it was. The first confirmed visitor from another star system. Oumuamua didn't look like anything we'd ever seen. It was shaped like a cigar, or maybe a pancake, somewhere between 300 and 1,000 feet long, far more elongated than any asteroid or comet in our solar system. Its surface was reddish, like objects in the outer reaches of our cosmic neighborhood. But here's where it gets strange. Oumuamua was moving too fast to have originated here. It was traveling at nearly 200,000 miles per hour. That's 54 miles every single second. For comparison, objects born in our solar system move at about 12 miles per second. Oumuamua was a vagabond, an interstellar wanderer. When scientists plotted its trajectory, they realized it had come from roughly the direction of the constellation Lyra. But because it had been traveling for hundreds of millions of years, the stars had moved since it started its journey. We'll never know exactly where it came from. Its home star, its place of origin, remains a mystery. Mystery 1. As Oumuamua moved away from the sun, astronomers noticed something odd. It was accelerating slightly, speeding up as it left. Comets do this because gases escaping from their surface give them a little push. But Oumuamua showed no signs of outgassing. No tail, no coma of dust and vapor. It looked like an asteroid, but behaved like a comet. Some scientists suggested it might be made of nitrogen ice or hydrogen ice. Others proposed more exotic explanations. One researcher even suggested, half seriously, that it could be an alien probe using the sun's gravity as a slingshot. Most astronomers now think Oumuamua was a comet after all, one with an unusual makeup. Cosmic rays hitting its surface over millions of years might have created pockets of trapped hydrogen inside its ice. When it warmed near the sun, that hydrogen escaped invisibly, pushing the object faster without creating a visible tail. But we'll never know for certain. Oumuamua is now past Neptune's orbit, heading back into the vast darkness between stars. It's gone. Mystery 2. Astronomers estimate that an object like Oumuamua passes through the inner solar system about once a year, but they're faint and hard to spot. Most slip by unnoticed. Within Neptune's orbit alone, there could be around 10,000 Oumuamua-sized interstellar objects right now, wandering through. Some have been here for years, others are just passing through, and we have no idea where most of them are. Are you still with me? Can you picture it? Our solar system isn't isolated. It's part of a galactic ocean, and objects drift through it constantly. Visitors from distant stars, each carrying secrets from places we'll never see. Let's zoom out a bit. Let's talk about signals. In 1977, a radio telescope in Ohio detected something extraordinary. A signal so strong, so clear, that the astronomer monitoring the data wrote "wow" in the margin. It's been called the WOW signal ever since. Mystery 3. The WOW signal lasted 72 seconds. It came from the direction of the constellation Sagittarius, near a group of stars called Chi Sagittarii. The signal's frequency was close to 1420 megahertz, right in the range where hydrogen emits naturally. And hydrogen is everywhere in the universe. The signal's intensity rose and fell exactly as you'd expect from something coming from a fixed point in space, as Earth's rotation carried the telescope's beam across it. But here's the mystery. The signal never repeated. Astronomers have searched that patch of sky hundreds of times since. Nothing. No follow-up. No second message. Some think it was a one-time natural event, maybe a magnetar flare or a collision between cosmic objects. Others wonder if it was artificial, a signal from an extraterrestrial civilization that happened to sweep past us once and never again. We don't know, and we may never know. Mystery 4. Since 2007, astronomers have detected something called fast radio bursts. These are incredibly brief flashes of radio waves, lasting just a few milliseconds. But in that fraction of a second, they release as much energy as the sun produces in 3 days. Think about that. 3 days of solar output, compressed into a few thousandths of a second. The first fast radio burst was discovered by Duncan Lorimer and his student in archived data. It's now called the Lorimer burst. Since then, hundreds more have been found. Some repeat, others happen once and vanish forever. Mystery 5. In 2022, astronomers detected a fast radio burst that repeated in a predictable pattern. It pulsed every 16.35 days. For about 4 days, it would send out bursts. Then it would go silent for 12 days. Then the cycle would repeat. This was the first repeating burst with a regular rhythm. It came from a galaxy about 500 million light-years away. Why does it pulse on a schedule? We're not sure. It might be orbiting something, like a neutron star circling a companion. Or it might be tied to some internal mechanism we don't understand. Mystery 6. Most fast radio bursts come from distant galaxies, billions of light-years away. But in 2020, astronomers detected one from within our own galaxy. It came from a magnetar, a type of neutron star with an incredibly powerful magnetic field. This was the closest fast radio burst ever detected, and it helped confirm that at least some of these signals come from magnetars. But not all. In January 2025, astronomers found a fast radio burst coming from a dead galaxy, a massive elliptical where star formation stopped billions of years ago. It was located far from the galactic center, in a region with no young stars. This shouldn't happen. Fast radio bursts are supposed to come from young, energetic environments. This one broke the rules. Mystery 7. In March 2025, astronomers detected the brightest fast radio burst of all time. They nicknamed it RBF LOTE, for Radio Brightest Flash of all time. It came from a galaxy only 130 million light-years away. That's cosmically close. It released as much energy as the sun produces in 4 days, but in less than a second. The burst came from the edge of a star-forming region, not the center. This suggests the source might be a slightly older magnetar, one that was kicked from its birthplace or formed just outside the main cluster. We're learning more about these bursts, but every new discovery raises new questions. Mystery 8. Some fast radio bursts travel through dense clouds of gas on their way to Earth. This gas acts like a lens, bending and filtering the radio waves. By studying how the signal scintillates or twinkles, astronomers can determine where the burst originated. For one burst, FRB 2022-1022A, scientists calculated that it must have come from a region only about 10,000 kilometers wide. That's extremely close to its source, probably within a few 100,000 kilometers of a rotating neutron star. But why do some neutron stars produce these bursts while others don't? Mystery 9. Let's shift to something stranger, something invisible. You've probably heard of dark matter. It's one of the biggest mysteries in all of science. Dark matter makes up about 27% of the universe. That's 5 times more than all the stars, planets, and gas we can see. But we can't see dark matter. It doesn't absorb, reflect, or emit light. It doesn't interact with electromagnetic radiation at all. We only know it's there because of gravity. Mystery 10. In the 1960s and 70s, astronomer Vera Rubin studied spiral galaxies. She measured how fast stars were moving as they orbited the galactic center. According to Newton's laws, stars farther from the center should move slower, just like planets farther from the sun orbit more slowly. But that's not what Rubin found. Stars at the edge of galaxies were moving just as fast as stars near the center, sometimes faster. This shouldn't be possible, unless there's more mass than we can see, a lot more. Rubin calculated that galaxies contain about 6 times more dark matter than visible matter. The stars we see are just the tip of the iceberg, Mystery 11. We don't know what dark matter is made of. The leading candidate is a hypothetical particle called a WIMP, which stands for Weakly Interacting Massive Particle. These particles would only interact through gravity and the weak nuclear force. They wouldn't interact with light at all. Scientists have built detectors deep underground, shielded from cosmic rays, hoping to catch a dark matter particle colliding with normal matter. So far, nothing. Decades of searching, and we haven't directly detected a single dark matter particle. Mystery 12. Some scientists think dark matter might not be particles at all. Maybe our understanding of gravity is wrong. Maybe gravity behaves differently on large scales than it does in our solar system. This idea is called modified Newtonian dynamics, or MOND. It suggests that when gravitational fields are extremely weak, like at the edges of galaxies, gravity doesn't follow the inverse square law anymore. It gets stronger. MOND can explain galaxy rotation curves without dark matter, but it struggles to explain other observations, like gravitational lensing. Most scientists still favor dark matter particles, but we're not certain. Mystery 13. Even if dark matter is real, we don't know if it's all the same thing. There might be multiple types of dark matter particles. Some could be heavy, others light. They might interact with each other in ways we don't understand. One idea suggests there's a hidden valley, a parallel world made of dark matter particles that interact with each other, but almost never with us. This hidden sector could have its own forces, its own chemistry. It could be as complex as the visible world, or more so, and we'd never see it directly. Mystery 14. Dark matter isn't evenly spread through the universe. It clumps. It forms structures. After the Big Bang, dark matter began gathering in long filaments, like a cosmic web. Normal matter fell into these gravitational wells, forming galaxies and galaxy clusters where dark matter was densest. So, in a way, dark matter is the scaffolding of the universe. Without it, galaxies wouldn't exist, stars wouldn't exist, we wouldn't exist, but we still don't know what it is. Does that seem strange to you? That most of the universe is made of something we can't see, can't touch, and don't understand? Let's keep going. There's something even stranger. Mystery 15. About 70% of the universe is made of dark energy, not dark matter, dark energy. It's even more mysterious. Dark energy is a force that's causing the universe to expand faster and faster. In the 1920s, Edwin Hubble discovered that distant galaxies are moving away from us. The farther away they are, the faster they're receding. This told us the universe is expanding. Scientists assumed this. Expansion would slow down over time because gravity pulls everything together. But in 1998, 2 independent teams measured the expansion rate more precisely. They found the opposite. The expansion is accelerating. Mystery 16. Whatever is causing this acceleration, we call it dark energy. It acts like anti-gravity, pushing space apart. Unlike dark matter, which clumps into galaxies, dark energy is spread evenly throughout the universe. It doesn't dilute as space expands. In fact, as the universe gets bigger, there's more dark energy, because there's more space, and dark energy is a property of space itself. Mystery 17. One possibility is that dark energy is Einstein's cosmological constant. Einstein added this to his equations of general relativity to keep the universe static, because he thought the universe wasn't expanding. When Hubble showed the universe was expanding, Einstein called the cosmological constant his biggest blunder. But now it's back. The cosmological constant would be a fixed property of empty space, a kind of baseline energy that exists everywhere. If that's what dark energy is, it means empty space isn't empty. It has energy, it has pressure, and that pressure pushes outward, causing expansion to accelerate. Mystery 18. But maybe dark energy isn't constant. Maybe it changes over time. This idea is called quintessence. Quintessence would be a field, like an electromagnetic field, that fills the universe. Its strength could vary from place to place or change as the universe ages. If dark energy is getting stronger, the universe's expansion will accelerate faster and faster until space itself is torn apart in what's called the Big Rip. If dark energy is getting weaker, expansion might slow down again. Eventually, gravity could take over and pull everything back together in a big crunch. We don't know which future awaits us. We're still measuring. Still watching. Mystery 19. Here's how much we know about the universe. 5% is ordinary matter. Everything we can see. Stars, planets, gas, dust, people. 27% is dark matter. Invisible, but we know it's there because of gravity. 68% is dark energy. Invisible, and we barely understand it at all. Put another way, 95% of the universe is made of things we can't see and don't fully understand. Think about that as you drift towards sleep. The universe you live in is mostly mystery, and that's not a bad thing. It means there's so much left to discover, so many questions still waiting for answers. We've covered 19 mysteries tonight, and we're just getting started. In the next part, we'll explore black holes and neutron stars, cosmic structures and ancient signals. But for now, rest. Let your mind wander through the dark matter scaffolding of the cosmos. Picture omuamua, tumbling through the void, carrying secrets from a star we'll never see. Imagine fast radio bursts flashing across billions of light years, each one a cosmic lighthouse. We're only beginning to understand. Sleep well, and when you wake, the universe will still be here, vast and strange and full of mysteries. If you're enjoying this journey, let me know in the comments. Which mystery intrigues you most so far? The wow signal? Oumuamua? Dark energy? I'd love to hear your thoughts. Welcome back. You're still here, drifting through these cosmic mysteries with me. We left off somewhere around Mystery 19, having explored interstellar visitors, fast radio bursts, and the invisible scaffolding of dark matter and dark energy that shapes our universe. Now, let's venture deeper. Let's talk about black holes. Mystery 20. Black holes are places where matter has been squeezed into such a small space that gravity becomes overwhelming. Nothing can escape from inside a black hole's event horizon, not even light. That's why they're black. But here's the strange part. We don't know what happens inside a black hole. Einstein's equations of general relativity predict a singularity at the center, a point of infinite density where the laws of physics break down. But does that singularity actually exist? Or does quantum mechanics prevent it somehow? We can't know. The event horizon is a one-way boundary. Information that crosses it can never come back to us. Black holes are, by design, forever mysterious. Mystery 21. In April 2019, astronomers unveiled the first image of a black hole. It wasn't a photograph in the usual sense. It was created by combining data from 8 radio telescopes around the world, forming what's called the Event Horizon Telescope. The image shows a glowing ring of superheated gas orbiting the supermassive black hole at the center of the galaxy M87. The black hole itself appears as a dark shadow in the middle. That shadow is about 40 billion kilometers across. The black hole has a mass of 6.5 billion suns, and yet, from our perspective here on Earth, it appears smaller than an orange held at arm's length on the surface of the moon. We had to build a telescope the size of the Earth just to see it. Mystery 22. Every large galaxy seems to have a supermassive black hole at its center. Our Milky Way has one. It's called Sagittarius, a star, and it has a mass of about 4 million suns. But here's the mystery. We don't know how these supermassive black holes got so big. Did they form from the collapse of massive stars and then grow by consuming gas and merging with other black holes? Or did they start big, forming directly from the collapse of enormous gas clouds in the early universe? Some quasars, which are powered by supermassive black holes, existed when the universe was less than 1 billion years old. That's not much time for a black hole to grow from stellar mass, maybe 10 or 20 suns, to billions of solar masses. The math is difficult. It requires the black holes to consume matter almost constantly, at the maximum possible rate. And even then, it's tight. We're not sure how they did it. Mystery 23. There's a relationship between the mass of a galaxy's central black hole and the speed at which stars orbit in the galaxy's outer regions. Bigger black holes live in galaxies where stars move faster. This relationship is called the M-sigma relation. But why does it exist? The black hole is tiny compared to the galaxy. It occupies a region maybe a few light days across. The galaxy spans hundreds of thousands of light years. How does the black hole know about the galaxy's overall properties? And how does the galaxy know how massive its central black hole should be? It suggests they grew together somehow, influencing each other over billions of years, but the details remain unclear. Mystery 24. In 2015, scientists detected gravitational waves for the first time. These are ripples in space-time itself, caused by violent cosmic events. The first detection came from 2 black holes, each about 30 times the mass of the Sun, spiraling into each other and merging. The collision released more energy in a fraction of a second than all the stars in the observable universe combined. But that energy wasn't light. It was gravitational waves, stretching and squeezing space as they passed through Earth. The detectors, called LIGO, measured a change in distance smaller than the width of a proton. Astonishing precision. Since then, dozens of black hole mergers have been detected. Each one teaches us something new. Mystery 25. Some black hole mergers don't fit expectations. In 2019, LIGO detected a collision between a black hole and something else. The companion object had a mass between 2 and 3 times the Sun. Too heavy to be a neutron star, which usually max out around 2 solar masses. Too light to be a typical black hole, which usually start around 5 solar masses. This object fell into what scientists call the mass gap. We didn't think anything could exist in that range, but here it was. Either our models of stellar evolution are wrong, or something unusual happened to create this object. Mystery 26. Let's talk about neutron stars. When a massive star runs out of fuel, its core collapses. If the core is too massive to become a white dwarf, but not quite massive enough to form a black hole, it becomes a neutron star. A neutron star is about 20 kilometers across. That's the size of a city, but it contains more mass than the Sun. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. The gravity is so intense that atoms are crushed. Protons and electrons merge into neutrons. The entire star becomes a giant atomic nucleus. Mystery 27. Some neutron stars are called pulsars. They spin incredibly fast and emit beams of radiation from their magnetic poles. As the star spins, those beams sweep across space like a lighthouse. If Earth happens to be in the path of the beam, we see a pulse of radio waves every time the star rotates. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell. The pulses were so regular that astronomers briefly wondered if they were signals from an alien civilization. They even nicknamed the source LGM-1 for little green men. But it turned out to be a natural phenomenon. A neutron star spinning 30 times per second. Mystery 28. We still don't fully understand what's inside a neutron star. At the surface, it's mostly neutrons. But deeper down, the pressure becomes unimaginable. Neutrons might break apart into their constituent quarks, forming what's called quark matter. Or the core might contain exotic particles we've never seen in laboratories. Some theories suggest strange matter made of up, down, and strange quarks in equal numbers. If strange matter is more stable than ordinary matter, a tiny seed of it could convert an entire neutron star into a strange star. And if a strange star collided with a normal neutron star, it might convert that one too. A cosmic infection spreading through the universe. Probably not. But we can't rule it out entirely, Mystery 29. In 2017, LIGO detected gravitational waves from two neutron stars merging. Unlike black hole mergers, this event also produced light. Gamma rays, X-rays, visible light, infrared. Telescopes around the world turned to observe. It was the first time astronomers witnessed both gravitational waves and electromagnetic radiation from the same event. The collision created heavy elements like gold and platinum. In fact, most of the gold on Earth probably came from neutron star mergers billions of years ago, before the solar system formed. You're wearing pieces of dead stars. Are you still with me? Can you picture it? Neutron stars so dense that a single cubic centimeter outweighs Mount Everest. Black holes so massive they anchor entire galaxies. Mystery 30. Some neutron stars are magnetars. Their magnetic fields are the strongest in the universe. A magnetar's field is about 1,000 trillion times stronger than Earth's. If you got within 1,000 kilometers of a magnetar, the magnetic field would be strong enough to distort the atoms in your body. Your molecular bonds would break. You'd dissolve. Magnetars occasionally release enormous bursts of energy called starquakes. The star's crust cracks and shifts, releasing magnetic energy in a violent flare. In December 2004, a magnetar called SGR 1806-20 released a flare so powerful that it affected Earth's ionosphere, even though the magnetar was 50,000 light-years away. For a tenth of a second, it was brighter than the full moon, but in gamma rays, we can't see. If it had been 10 light-years away, it would have caused a mass extinction on Earth. Mystery 31. Black holes are supposed to be eternal. Once something falls in, it's gone forever. But in the 1970s, Stephen Hawking showed that black holes can evaporate. Quantum effects near the event horizon cause the black hole to emit radiation, now called Hawking radiation. Over incredibly long timescales, this radiation carries away the black hole's mass. Eventually, after a time far longer than the current age of the universe, even supermassive black holes will evaporate completely. But here's the problem. Hawking radiation is thermal. It's random. It doesn't carry information. If a black hole evaporates, what happens to the information about everything that fell in? Quantum mechanics says information can't be destroyed, but black hole evaporation seems to destroy it. This is called the black hole information paradox. Mystery 32. Some physicists think information isn't destroyed. Maybe it's encoded on the event horizon like a hologram, or maybe it escapes in subtle correlations in the Hawking radiation. Others suggest that black holes leave behind remnants, tiny stable objects that contain all the information but no longer have event horizons. We don't know. To solve this, we'd need a theory of quantum gravity, combining quantum mechanics and general relativity. We don't have that yet, Mystery 33. Let's zoom out again. The universe isn't uniform. Galaxies aren't scattered randomly. They're organized into enormous structures. Galaxies cluster into groups and clusters. Clusters gather into superclusters. And superclusters are arranged along filaments of dark matter, creating what's called the cosmic web. Between the filaments are vast voids, regions with almost no galaxies at all. The largest structures in the universe span hundreds of millions of light-years. Why does the universe have this structure? It goes back to the early universe. Tiny fluctuations in density, seeded during cosmic inflation, grew over billions of years. Regions that were slightly denser pulled in more matter through gravity, becoming denser still. Eventually, they formed galaxies and clusters. But the details of how this happened are still being worked out. Mystery 34. In 2013, astronomers discovered the Hercules Corona Borealis Great Wall. a structure made of galaxy clusters stretching across 10 billion light-years. That's more than 10% of the observable universe's diameter. According to cosmological models, structures this large shouldn't exist. The universe hasn't been around long enough for gravity to pull together something so vast. And yet, there it is. Either our models are missing something, or this structure formed through processes we don't understand. Mystery 35. Saturn has a strange moon called Hyperion. It's irregularly shaped like a sponge and covered with deep craters. But here's the odd part. Hyperion is charged with static electricity. NASA's Cassini spacecraft detected a beam of particles flowing away from the moon into space. Scientists think cosmic rays and solar wind knock electrons off the surface, leaving it with a net positive charge. But why Hyperion and not other moons? We're not entirely sure. Mystery 36. Saturn itself has mysteries. Its magnetic field is almost perfectly aligned with its rotation axis. For Earth, Jupiter, and most other planets, the magnetic axis is tilted relative to the rotation axis. That tilt helps scientists figure out how fast the planet's interior is rotating. But Saturn's alignment makes it impossible to measure the deep interior's rotation rate. We know how fast the clouds rotate. We don't know how fast the planet itself spins underneath. After decades of study, we still can't answer this basic question. Mystery 37. Saturn's moon Iapetus has a ridge running along its equator. The ridge is about 1,200 kilometers long and 20 kilometers high in places. No other moon in the solar system has anything like it. Why is it there? Some think Iapetus rotated much faster when it was young and molten. The rapid spin caused it to bulge at the equator. When it cooled and slowed down, the bulge froze in place. Others think the ridge is made of material that fell from Saturn's rings over billions of years, piling up along the equator. We have hypotheses. We don't have certainty. Mystery 38. The moon also holds mysteries. Parts of the moon's crust have magnetic fields, but the moon has no global magnetic field today. It doesn't have a molten core generating magnetism like Earth does. So, where did these local magnetic patches come from? One idea is that asteroid impacts scattered magnetic materials across the surface billions of years ago. Another suggests the moon once had a magnetic field, generated by a core that has since cooled and solidified. The magnetism we detect today would be fossilized remnants. Either way, it's strange. Mystery 39. Our solar system is odd in some ways. The inner planets, Mercury, Venus, Earth, and Mars, are small and rocky. The outer planets, Jupiter, Saturn, Uranus, and Neptune, are gas and ice giants. This arrangement makes sense. Close to the Sun, it's too hot for ice to condense, so only rock and metal accumulated. Farther out, ice could form, allowing planets to grow much larger. But when we look at exoplanets, planets around other stars, we find all kinds of arrangements. Hot Jupiters orbit closer to their stars than Mercury is to the Sun. Super-Earths, rocky planets several times more massive than Earth, are common. We don't have any in our solar system. Why is our system different? Was it chance? Or is there something special about the conditions that allowed life to arise here? Mystery 40. Let's talk about cosmic rays. These are high-energy particles, mostly protons, that zip through space at nearly the speed of light. They come from all directions, constantly bombarding Earth. Our atmosphere shields us from most of them. But where do they come from? Most cosmic rays probably come from supernova explosions. When a massive star explodes, it accelerates particles to tremendous energies. But some cosmic rays have energies far higher than any supernova should produce. These are called ultra-high energy cosmic rays. In 1991, a particle called the Oh My God particle struck Earth's atmosphere. It carried as much kinetic energy as a baseball thrown at 60 miles per hour in a single subatomic particle. We don't know what could accelerate particles to such energies. Supermassive black holes? Colliding. Galaxies? Exotic physics we haven't discovered yet? We've covered 21 more mysteries tonight. 40 in total so far. Black holes that might not have singularities. Neutron stars made of quark soup. A cosmic web spanning billions of light years. The oh my god particle, each one a question mark floating in the dark. Rest now. Let your thoughts drift among pulsars and magnetars, spinning lighthouses in the cosmic sea. Picture the gravitational waves rippling past us, messages from collisions we'll never witness directly. Sleep gently. And if you're still curious when you wake, we'll continue this journey. There are 60 mysteries yet to come. Which of tonight's mysteries surprised you most? The mass gap object? The static electricity on Hyperion? The ridge on Iapetus? Let me know in the comments. Good night. You're still here. Good. We're going deeper now into the strange architecture of space-time, the peculiar behavior of light, and objects that challenge everything we thought we knew. We've explored 40 mysteries so far. Let's continue. Mystery 41. In 2012, astronomers discovered the first repeating fast radio burst, FRB 11102. Most fast radio bursts happen once and disappear, but this one kept flashing. Over months and years, it sent out dozens of bursts. When scientists finally pinpointed its location, they found it embedded in an extreme environment. A dwarf galaxy 3 billion light-years away, surrounded by a persistent glow of radio emission and an incredibly strong magnetic field. No other fast radio burst source looked like this. It suggested that repeating and non-repeating bursts might come from different types of objects entirely. Mystery 42. In 2020, astronomers reported detecting 8 more repeating fast radio burst sources. Each one had its own pattern. Some repeated regularly, others sporadically. The bursts from repeating sources lasted slightly longer and emitted more focused frequencies than one-off bursts. This strengthened the idea that there are at least 2 distinct populations of fast radio bursts, each produced by different mechanisms. But what those mechanisms are remains uncertain. Mystery 43. Tabby's star, officially known as KIC 8462852, exhibits the strangest behavior astronomers have ever recorded in a star. Located 1,470 light-years away in the constellation Cygnus, this F-type star dims irregularly. Sometimes it blocks up to 22% of its light. That's enormous. When a planet passes in front of a star, it typically blocks less than 1%. The dips in Tabby's star's brightness have no pattern. They're erratic, unpredictable. Some evidence suggests the star has been gradually dimming over the past century. Scientists have proposed many explanations. A swarm of comets, fragments from a shattered planet, circumstellar dust from colliding asteroids. None fully account for the dramatic, irregular dimming. One astronomer even suggested, mostly as a thought experiment, that it could be a megastructure built by an advanced civilization. Probably not, but the star keeps defying easy explanation. Mystery 44. In 2019, radio astronomers discovered something they called odd radio circles, or ORCs. These are enormous ring-shaped structures that span roughly 1 million light-years across. They emit only in radio wavelengths, making them invisible to optical telescopes. They have sharp, well-defined edges that suggest a sudden, powerful event, rather than gradual formation. No one had seen anything like them before. Scientists have proposed several ideas. Maybe they're shock waves from galaxy mergers. Maybe they're the remnants of massive explosions in galactic cores. Or perhaps there's something entirely new, a phenomenon we haven't categorized yet. As of now, only a handful have been found. We're still trying to understand what they are. Mystery 45. The center of our galaxy is home to something called the Fermi bubbles. These are 2 enormous lobes of high-energy gamma radiation extending 25,000 light-years above and below the Milky Way's center. They're invisible to human eyes, but they blaze brightly in gamma-ray observations. Their edges are sharp and well-defined, suggesting they formed from a sudden explosion rather than gradual stellar activity. What caused them? The leading theories involve violent outbursts from Sagittarius A star, our galaxy's central black hole, or intense bursts of star formation near the galactic core millions of years ago. Either way, something dramatic happened, and we're still seeing the aftermath. Mystery 46. Let's talk about cosmic inflation. In the first fraction of a second after the Big Bang, the universe expanded exponentially. Space itself stretched faster than the speed of light, growing from smaller than an atom to larger than a galaxy in less than a trillionth of a second. This theory, called cosmic inflation, explains why the universe looks smooth and uniform on large scales. Without inflation, different regions of the universe would never have been in contact with each other, so they shouldn't have the same temperature. But they do. Inflation smoothed everything out. But we don't know what caused inflation. We call it the inflaton field. But we don't know what the inflaton is or where it came from. And we don't know why inflation stopped. Mystery 47. The cosmic microwave background is the oldest light in the universe. It's the afterglow of the Big Bang, released when the universe was only 379,000 years old. Before that, the universe was too hot for atoms to form. It was an opaque plasma of electrons and protons. But when it cooled enough, electrons and protons combined into hydrogen atoms. Light could finally travel freely. That light has been traveling through space ever since, stretched by cosmic expansion into microwaves. We can detect it in every direction. It's almost perfectly uniform, with temperature variations of only a few millionths of a degree. But those tiny variations are important. They represent the seeds of all structure in the universe. Regions that were slightly denser became galaxies. Regions that were slightly less dense became voids. Mystery 48. There's a pattern in the cosmic microwave background that scientists call the axis of evil. Not because it's sinister, but because it's unexpected. Some large-scale features in the microwave sky appear to be aligned with the motion and orientation of our solar system. This shouldn't happen. The cosmic microwave background comes from 13.8 billion years ago, from all over the universe. It should have no relationship to the solar system, which formed only 4.5 billion years ago. This alignment just a coincidence? Is it due to errors in how we process the data? Or does it violate the Copernican principle, the idea that our location in the universe isn't special? We're not sure. Mystery 49. Gamma-ray bursts are some of the most powerful explosions in the universe. For a few seconds or minutes, a gamma-ray burst can outshine every star in its galaxy combined. They come in two types. Short bursts, lasting less than 2 seconds, probably come from neutron star mergers. Long bursts, lasting more than 2 seconds, come from the deaths of massive stars, supernovae with a particular twist. When the star's core collapses, it forms a black hole. Material falling into the black hole generates jets of energy that punch through the star and blast into space. If one of those jets happens to point toward Earth, we see a gamma-ray burst. But here's the mystery. Some gamma-ray bursts are far more energetic than our models predict. They release more energy than a supernova should be able to produce. And occasionally, they come from unexpected places, like old galaxies where massive stars shouldn't exist. Mystery 50. In 2022, astronomers detected a gamma-ray burst that lasted over 7 hours. Most long bursts last a few minutes at most. This one kept going. It was unlike anything scientists had seen before. It might have come from the birth of a black hole in a rare type of collapse. Or it could represent an entirely new class of cosmic event. We're still analyzing the data. Can you feel the scale of these mysteries? Events so powerful they light up entire galaxies. Signals so faint we almost missed them. Patterns in ancient light that might reveal the universe's deepest secrets. Mystery 51. The universe is expanding. We know this, but how fast is it expanding? Scientists measure this using something called the Hubble constant. It's named after Edwin Hubble, who discovered cosmic expansion in the 1920s. But here's the problem. Different methods of measuring the Hubble constant give different answers. When astronomers measure nearby supernovae and use them to calculate expansion, they get one number. When they study the cosmic microwave background and extrapolate forward, they get a different number. The discrepancy is small, but it's real and significant. This is called the Hubble tension. Either our measurements have systematic errors we haven't identified, or there's new physics we don't understand. Maybe the expansion rate has changed in unexpected ways. Maybe dark energy is more complicated than we thought. Mystery 52. The observable universe is 93 billion light-years across, but the universe is only 13.8 billion years old. How can something be bigger than the distance light could have traveled? The answer is expansion. Space itself has been stretching. Light from distant galaxies has been traveling toward us for billions of years, but during that time, space expanded. The galaxies moved farther away even as their light traveled toward us. So the observable universe is much larger than 13.8 light-years across. But here's the real mystery. What's beyond the observable universe? If space is infinite, then the universe is infinite. If it's finite but unbounded, like the surface of a sphere, it wraps around on itself. We don't know which is true. We may never know. Mystery 53. The baryon asymmetry problem asks a simple question. Why is there more matter than antimatter? When matter and antimatter meet, they annihilate, releasing energy. In the Big Bang, equal amounts of matter and antimatter should have been created. They should have annihilated each other completely, leaving only energy. But clearly, that didn't happen. We're made of matter. So are stars and galaxies. There must have been a slight imbalance. For every billion antimatter particles, there were 1,000,001 matter particles. The billion pairs annihilated. The extra matter survived and became everything we see. But why was there an imbalance? What process favored matter over antimatter? We have theories. None are confirmed. Mystery 54. The oh my god particle we mentioned earlier raises deeper questions. If cosmic rays can reach such extreme energies, there should be a theoretical limit called the GZK cutoff. Above this energy, cosmic rays interact with the cosmic microwave background radiation, losing energy and creating other particles. They shouldn't be able to travel far, so ultra-high energy cosmic rays should come from nearby, cosmically speaking. But we haven't identified their sources. And some cosmic rays exceed the GZK cutoff by large margins. How do they maintain such energy? Where do they come from? Mystery 55. Let's return to our solar system briefly. There's a hypothetical ninth planet, sometimes called Planet 9 or Planet X. Astronomers haven't seen it. But several distant objects in the outer solar system have strange, clustered orbits. Their paths are tilted and elongated in similar ways. This could be random chance, or it could be the gravitational influence of an unseen planet. If Planet 9 exists, it would be about 5 to 10 times Earth's mass, orbiting far beyond Neptune. Searches are ongoing. So far, nothing. Either the planet is too faint to detect with current telescopes, or the orbital clustering is coincidental. We're looking. Mystery 56. In 1977, the Voyager spacecraft launched, carrying golden records with sounds and images from Earth. Messages to any extraterrestrial intelligence that might find them. Voyager 1 is now over 15 billion miles from Earth, traveling through interstellar space. It's the most distant human-made object, and it's still sending signals, faint but detectable. Voyager has revealed mysteries of its own. When it crossed into interstellar space, it detected a faint background hum, a subtle plasma wave signal that no one expected. The space between stars isn't silent, it hums. Mystery 57. Enceladus, one of Saturn's moons, has geysers erupting from its south pole. They shoot water ice and vapor into space. Beneath Enceladus's frozen surface lies a global ocean of liquid water, heated by tidal forces from Saturn's gravity. The ocean is in contact with a rocky core. That combination, liquid water, heat, and minerals, could potentially support life. Cassini spacecraft flew through the geysers and analyzed the particles. It found organic molecules, complex carbon compounds. Does life exist in Enceladus's ocean? We don't know, but the ingredients are there. Mystery 58. Europa, one of Jupiter's moons, also has a subsurface ocean, bigger than Enceladus's. Deeper, too. The ice shell above the ocean might be tens of kilometers thick, but there's evidence of water plumes erupting from cracks in the ice, similar to Enceladus. NASA is planning a mission called Europa Clipper to study the moon in detail. It will search for signs of habitability, maybe even biosignatures, chemical traces that life might produce. But even if we find them, we won't know for sure unless we go beneath the ice. And that's a challenge for future generations. Mystery 59. Titan, Saturn's largest moon, is the only moon in the solar system with a thick atmosphere. It's mostly nitrogen, like Earth's, with clouds of methane and ethane. Liquid methane rains from the sky, carving rivers and filling lakes. The surface is frozen, but beneath it might be an ocean of liquid water mixed with ammonia. Titan's chemistry is complex. Organic molecules form in the atmosphere and drift down to the surface, building up over millions of years. Could life exist in Titan's methane lakes? Life as we know it requires water, but maybe there are other forms of biochemistry, exotic metabolisms we haven't imagined. Titan might host the strangest life in the solar system if it's there at all. Mystery 60. The Fermi paradox asks a profound question. Where is everybody? The universe is vast. Billions of galaxies, each with billions of stars. Many of those stars have planets. Some planets are in the habitable zone, where liquid water could exist. If life arose on Earth, it could arise elsewhere. And if intelligent life evolved here, it might evolve elsewhere too. But we see no signs of extraterrestrial civilizations. No megastructures. No radio signals. No interstellar probes visiting our solar system. Why? Are we alone? Did life arise here by an incredibly rare fluke? Or do civilizations tend to destroy themselves before they spread to the stars? Maybe interstellar travel is harder than we think. Maybe intelligent species don't build radio transmitters. Or maybe they're out there, quiet and hidden, and we just haven't looked in the right way yet. We've reached Mystery 60. 40 more to go. Rest now. Let your thoughts wander through subsurface oceans and methane lakes, through the silence of the Fermi paradox and the hum of interstellar plasma. Sleep gently. There's so much more waiting. You're back. We've crossed the halfway point now, 60 mysteries behind us. Let's keep moving through this cosmic catalog of questions. From the quantum realm to the edges of perception, there are 40 more waiting. Mystery 61. Quantum entanglement is one of the strangest phenomena in physics. When two particles become entangled, measuring one instantly affects the other, no matter how far apart they are. Einstein called it spooky action at a distance. He didn't like it. He thought it violated the speed of light limit. But experiments have confirmed it repeatedly. Entangled particles remain connected across any distance. If you measure one particle's spin, the other particle's spin immediately becomes determined, even if it's on the other side of the galaxy. How does this happen without information traveling faster than light? We don't fully know. Quantum mechanics allows it, but the mechanism feels deeply counterintuitive. Mystery 62. The double-slit experiment reveals the wave-particle duality of light and matter. If you shine light through two narrow slits, it creates an interference pattern on a screen behind them, as if light were a wave. But if you try to detect which slit the light passes through, the interference pattern disappears. Light behaves like particles. The act of observation changes the outcome. This isn't just about light. Electrons do it, atoms do it, Even large molecules have shown wave-like behavior. What's going on? Does observation collapse a quantum wave function? Or do multiple realities branch off, each with a different outcome? Interpretations vary. The mystery remains. Mystery 63. The measurement problem in quantum mechanics asks when and how a quantum system transitions from a superposition of states to a single definite state. Before measurement, a particle exists in all possible states simultaneously. After measurement, it's in one state. What causes the collapse? Some physicists think consciousness plays a role. Others think it's just interaction with the environment. Many worlds' interpretations suggest there's no collapse at all. Every possibility happens, each in its own branch of reality. We experience one branch, unaware of the others. Which interpretation is correct? We don't know. They all predict the same experimental results. Mystery 64. Let's talk about the cosmological constant problem. In quantum field theory, empty space isn't empty. It's filled with virtual particles constantly popping in and out of existence. These quantum fluctuations should contribute to the energy of space. When physicists calculate how much energy this adds, they get a number. A very large number. But when astronomers measure dark energy, the actual energy of empty space, they get a much smaller number. How much smaller? About 120 orders of magnitude smaller. That's a 1 followed by 120 zeros. It's the worst prediction in the history of physics. Either our calculation is fundamentally wrong, or there's a mechanism that cancels out almost all the vacuum energy, leaving just a tiny residue. We don't know what that mechanism would be. Mystery 65. Supersymmetry, or SUSY, is a theory that proposes every particle in the Standard Model has a heavier superpartner. Electrons have selectrons, quarks have squarks, photons have photinos. If supersymmetry is real, it could solve several problems at once. It could explain dark matter, it could unify the fundamental forces, it could stabilize the Higgs boson's mass. But despite decades of searching, no superpartners have been detected. The Large Hadron Collider has looked. Nothing. Either supersymmetry doesn't exist, or the superpartners are heavier than we thought, beyond the reach of current experiments. Mystery 66. String theory suggests that the fundamental constituents of reality aren't point-like particles, but tiny vibrating strings. Different vibration modes correspond to different particles. Strings could unify quantum mechanics and general relativity, giving us a theory of quantum gravity. But string theory requires extra dimensions. Not just the 3 spatial dimensions we experience, but 6 or 7 more. Curled up so small we can't see them. And there are many possible ways to curl up those dimensions, leading to a vast landscape of possible universes, each with different physical laws. We might live in just one of countless possibilities, and string theory hasn't made testable predictions yet. It's elegant mathematics, but we don't know if it describes reality. Mystery 67. The black hole information paradox isn't just about information, it challenges the foundations of physics. Quantum mechanics says information is conserved. General relativity says black holes destroy information. Both theories are incredibly successful, but they can't both be right. Some physicists think the solution lies in a concept called black hole complementarity. Information isn't lost. It's encoded on the event horizon in a way that looks different to observers inside and outside the black hole. Others think firewalls form at the horizon, destroying anything that crosses. But firewalls violate general relativity's equivalence principle. We're stuck. The paradox remains unsolved. Mystery 68. Dark matter might interact with itself through forces we don't know about. Most models assume dark matter only interacts through gravity. But what if there's a dark force, like electromagnetism, that only dark matter particles feel? This could lead to dark atoms, dark molecules, even dark chemistry. A hidden sector of reality running parallel to ours. Invisible, but present. Some observations of galaxy collisions hint at this. When 2 clusters collide, the dark matter usually passes through cleanly, But in a few cases, it seems to lag behind, as if dark matter particles interacted and slowed each other down. Mystery 69. Quasars are among the brightest objects in the universe. They're powered by supermassive black holes consuming enormous amounts of matter. The material forms a disk around the black hole, heating up to millions of degrees and emitting intense radiation. Some quasars are so luminous they outshine entire galaxies. But here's the mystery. Quasars were common when the universe was young. Billions of years ago, they were everywhere. Today, they're rare. Why? Did galaxies run out of gas to feed their central black holes? Did something change in how galaxies evolved? And why do some galaxies have active quasars while others, seemingly similar, don't? Mystery 70. The Great Attractor is a gravitational anomaly in intergalactic space. Our Milky Way, along with hundreds of thousands of other galaxies, is being pulled toward it. The Milky Way is moving at about 600 kilometers per second in the direction of the constellation Centaurus. But we can't see the Great Attractor directly. It's hidden behind the disk of our galaxy, obscured by dust and stars. We know something massive is there, pulling us. It might be a supercluster of galaxies, or a concentration of dark matter. But the details are hidden. Mystery 71. Beyond the Great Attractor lies something even larger. The Shapley Supercluster, one of the most massive structures in the nearby universe. It contains thousands of galaxies and exerts a gravitational pull even stronger than the Great Attractor. We're falling toward it too. Our entire local group of galaxies is caught in a flow of cosmic traffic, drawn toward these massive structures. Where will we end up? In billions of years, we might merge with the Shapley Supercluster. Or maybe the expansion of the universe will carry us apart before we get there. The future is uncertain. Mystery 72. Rogue planets drift through interstellar space, untethered to any star. They were either ejected from their planetary systems by gravitational interactions or formed alone in the depths of molecular clouds. We've detected a few, but there could be billions in our galaxy, maybe even more rogue planets than stars. They're cold, dark, and lonely, traveling through the void. Some might have moons. If a rogue planet has enough internal heat, perhaps from radioactive decay or tidal forces from a large moon, it could support subsurface oceans. Life might exist on a planet that never sees a sun. Unlikely, but not impossible. Mystery 73. In 2018, astronomers discovered a very distant object in our solar system. They called it Farfarut. It's currently 92 times farther from the Sun than Earth is. At its most distant, it reaches 140 astronomical units. It takes about 1,000 years to orbit the Sun. Farfarut is tiny, maybe 400 kilometers across, but its orbit is strange, highly elliptical, suggesting it might have been scattered by the gravity of Neptune or another planet. How many objects like Farfarut are out there, we don't know. The outer solar system is vast and poorly explored. Mystery 74. The Kuiper Belt, beyond Neptune, is home to countless icy bodies. Pluto is one, but there are others, some nearly as large. And beyond the Kuiper Belt lies the Oort cloud, a vast sphere of comets surrounding the solar system at distances up to 100,000 astronomical units. We've never seen the Oort cloud directly. We infer its existence from the comets that occasionally fall inward toward the Sun. But what's out there? Are there larger objects, dwarf planets we haven't detected? Could Planet 9 be hiding in the Oort cloud? Mystery 75. Comets are time capsules from the early solar system. They formed far from the Sun, in cold regions where ice could persist. Their composition hasn't changed much in 4.5 billion years. When a comet approaches the Sun, ice sublimates, creating a glowing coma and tail. But some comets behave strangely. Comet Borisov, the second interstellar visitor detected, looked like a normal comet. It had a tail. It outgassed. it fit expectations. But other comets fragment unexpectedly, or brighten and dim in unusual patterns. Each one is different. Mystery 76. Amino acids, the building blocks of proteins, have been found in meteorites. Comets contain organic molecules. The ingredients for life are scattered throughout space. Does that mean life is common? Or are we a rare accident? The Drake equation tries to estimate the number of communicative civilizations in the galaxy. It multiplies together factors like the star formation rate, the fraction of stars with planets, the number of habitable planets per system, the fraction where life arises, the fraction where intelligence evolves, and the fraction that developed technology. Depending on what values you plug in, you get anywhere from 0 to millions of civilizations. We don't know which is right. Mystery 77. The wow signal, which we talked about earlier, remains unexplained. But there are other mysterious signals too. In 2019, astronomers detected a radio signal from Proxima Centauri, the closest star to the Sun. It had a narrow frequency band, unusual for natural sources. It shifted in frequency in a way consistent with a planet orbiting the star. But follow-up observations found nothing. The signal didn't repeat. Was it interference from Earth-based technology or something else? We're not sure. Mystery 78. The cosmic microwave background has cold spots, regions slightly cooler than average. One particularly large cold spot, about 1.8 billion light-years across, has puzzled cosmologists. It might be a statistical fluke, or it could be the signature of a supervoid, a vast region of space with less matter than average. Light passing through it would lose energy, appearing cooler. But even accounting for this, the cold spot is larger than expected. Some have speculated it could be evidence of a collision between our universe and another in a multiverse. Unlikely, but intriguing. Mystery 79. The multiverse hypothesis suggests our universe is one of many. In eternal inflation models, inflation never fully stops. It ends in some regions, creating bubble universes, but continues elsewhere. Each bubble could have different physical constants, different particles, different laws. We'd only exist in a bubble where the conditions allow life. This is called the anthropic principle. But if the multiverse exists, we can never observe other universes. They're beyond our cosmic horizon, forever inaccessible. Is the multiverse science or philosophy? The debate continues. Mystery 80. Hawking radiation, if it exists, is too faint to detect from astrophysical black holes. But physicists have created analogs in the lab. Sonic black holes, formed in fluids where sound waves can't escape a certain region, might emit an analog of Hawking radiation. Early experiments suggested they do, but confirming it is difficult. If we can prove Hawking radiation exists in these analogs, it strengthens our confidence that it exists in real black holes too. We've reached 80, 20 left. Rest your mind. Let it drift among rogue planets and interstellar comets, through the multiverse and the cold spots in ancient light. Sleep softly. When you return, we'll finish this journey together. We're nearing the end now. 80 mysteries explored, 20 more waiting. Let's bring this journey home gently, moving through the final questions that make the universe strange and beautiful and endlessly fascinating. Mystery 81. White dwarfs are the remnants of stars like the sun. When a star exhausts its nuclear fuel, it sheds its outer layers and leaves behind a dense core about the size of Earth, but with the mass of the sun. White dwarfs cool slowly over billions of years, eventually fading into black dwarfs, cold and dark. But the universe isn't old enough yet for any black dwarfs to exist. Every white dwarf is still glowing, faintly. Some white dwarfs are very old, older than the Milky Way's disk. They formed in the early universe, when galaxies were still assembling. Their existence hints at an earlier era of star formation, a deeper history written in cooling embers. Mystery 82. Type Ia supernovae occur when white dwarfs accumulate too much mass, usually by pulling material from a companion star. When a white dwarf exceeds about 1.4 solar masses, it can no longer support itself. It collapses, triggering runaway nuclear fusion. The entire star explodes. Because all Type Ia supernovae explode at roughly the same mass, they release similar amounts of energy. This makes them useful as standard candles for measuring cosmic distances. But we don't fully understand the details. Do all Type Ia supernovae come from white dwarfs with companions? Or can two white dwarfs merge and explode? The mechanisms are still debated. Mystery 83. Pulsars slow down over time as they lose rotational energy, but occasionally a pulsar suddenly speeds up. These events are called glitches. The pulsar's crust cracks and shifts, transferring angular momentum from the interior to the surface. For a brief moment, the pulsar spins faster, then it gradually slows down again. Glitches reveal something about neutron star interiors, but the details are murky. What's happening beneath that crust? How do the superfluid and the solid crust interact? Mystery 84. Pulsars also emit pulses with astonishing regularity. Some pulsars keep time better than atomic clocks. Astronomers use them to test general relativity and search for gravitational waves. An array of pulsars scattered across the sky acts like a galaxy-sized detector, sensitive to the low-frequency gravitational waves from supermassive black hole mergers. But recently, timing irregularities have appeared in some pulsar data. Are we detecting gravitational waves? Or is it noise from interstellar plasma? The analysis is ongoing. Mystery 85. Brown dwarfs are objects too massive to be planets, but not massive enough to sustain hydrogen fusion like stars. They're sometimes called failed stars. They glow faintly from leftover heat from their formation and from deuterium fusion, which happens briefly in their youth. Brown dwarfs blur the line between planets and stars. Where do you draw the boundary? Is it based on mass, formation mechanism, composition? The answer isn't obvious. Mystery 86. Some brown dwarfs have atmospheres with clouds of molten iron or silicate dust. They have weather, storms of liquid metal, winds that circle the object at hundreds of meters per second. Studying brown dwarfs helps us understand giant exoplanets, which often have similar atmospheres. But brown dwarfs are easier to study because they're not overwhelmed by the light of a nearby star. Mystery 87. Exoplanets come in stunning variety. Hot Jupiters, gas giants orbiting closer to their stars than Mercury is to the Sun. Super-Earths, rocky worlds more massive than Earth but smaller than Neptune. Mini-Neptunes, ice giants with thick atmospheres. Planets orbiting binary stars. Planets with orbits so eccentric they swing from oven to freezer every orbit. Why is there such diversity? How do planets form and migrate? We're building models, but each new discovery challenges them. Mystery 88. Some exoplanets orbit in the habitable zone, the region where liquid water could exist on the surface. But being in the habitable zone doesn't guarantee habitability. A planet needs the right atmosphere, the right mass, the right geology. Mars is in the Sun's habitable zone, but it's a frozen desert. Venus is at the inner edge, but its greenhouse effect makes it hellish. Habitable zones are starting points, not guarantees. Mystery 89. The James Webb Space Telescope is studying exoplanet atmospheres. By watching how starlight filters through a planet's atmosphere during a transit, astronomers can detect molecules: water vapor, methane, carbon dioxide, oxygen. If we find oxygen and methane together, that could hint at biological activity, but it's not proof. Geology can produce similar signatures. We'll need detailed observations of many planets before we can say anything definitive. Mystery 90. In 2015, astronomers discovered a star called KIC 8462852, Tabby's star, which we mentioned earlier. But there's more to the story. In 2017, Tabby's star dimmed again, and astronomers around the world coordinated observations. They found that the dimming was more pronounced in blue light than in red light. This suggested dust, not a solid object, was blocking the starlight. But where did the dust come from? And why does it block so much light so irregularly? The mystery deepened instead of resolving. Mystery 91. In our own solar system, the asteroid belt between Mars and Jupiter contains millions of rocky fragments. But the total mass of all asteroids combined is less than the Moon's mass. That's strange. Early models predicted the asteroid belt should contain much more material. What happened? Jupiter's gravity probably scattered most of it, ejecting material or sending it crashing into planets. The asteroids we see are leftovers, remnants of a planet that never formed. Mystery 92. Some asteroids have moons, tiny satellites orbiting larger rocks. How did they form? Did the asteroids capture passing objects? Or did collisions split asteroids into pieces that stayed gravitationally bound? Each system is different. Each has its own history. Mystery 93. In 2014, the Rosetta spacecraft landed a probe on Comet 67P Churyumov-Gerasimenko. The mission revealed complex organic molecules, including glycine, an amino acid. It found molecular oxygen in the coma, which was unexpected. And it discovered that the comet's water had a different isotopic ratio than Earth's oceans. This suggested that comets like 67P didn't deliver most of Earth's water. Maybe asteroids did. Or maybe Earth's water came from the solar nebula during formation. The question remains open. Mystery 94. Phosphine, a chemical associated with biological activity on Earth, was detected in Venus's atmosphere in 2020. The announcement sparked excitement and controversy. Follow-up observations were inconclusive. Some teams confirmed the detection, others found nothing. If phosphine is really there, it's a puzzle. Venus's surface is hot enough to melt lead. The atmosphere is thick with sulfuric acid clouds. How could anything live there? Maybe the detection is wrong, or maybe there's a chemical process we don't understand. Or just maybe, microbial life floats in Venus's cooler upper atmosphere. Mystery 95. Mars has methane in its atmosphere. Not a lot, but enough to detect. Methane breaks down quickly under ultraviolet light, so if it's present, something must be replenishing it. On Earth, methane comes from both geological processes and biological activity. On Mars, we don't know. Rovers have measured methane spikes, sudden increases that appear and disappear. The source could be subsurface reservoirs releasing gas through cracks, or it could be microbial life deep underground. We won't know until we dig deeper. Mystery 96. Jupiter's moon Ganymede has a magnetic field, the only moon in the solar system with one. This suggests Ganymede has a liquid iron core, still hot enough to generate magnetism through dynamo action. Beneath Ganymede's icy surface lies a subsurface ocean, sandwiched between layers of ice. Could life exist there? The ocean might be isolated from the surface, cut off from nutrients. Or maybe hydrothermal vents on the ocean floor provide energy. We don't know. Mystery 97. Saturn's rings are made of ice particles, ranging from dust grains to house-sized boulders. They're thin, only about 10 meters thick in most places, but they span hundreds of thousands of kilometers. How did they form? One theory suggests they're the remnants of a moon that wandered too close and was torn apart by tidal forces. Another suggests they're leftover material from Saturn's formation. Recent observations from Cassini suggest the rings are relatively young, only a few 100 million years old. But if that's true, why did they form so recently? Mystery 98. Uranus and Neptune are ice giants, distinct from Jupiter and Saturn. Their interiors contain water, methane, and ammonia ices under extreme pressure. These materials might form superionic ice, a strange state where oxygen atoms are locked in a crystal lattice while hydrogen atoms flow freely like a liquid. Superionic ice conducts electricity. It could explain the planet's unusual magnetic fields, which are tilted and offset from their centers. But we've only visited these planets once, briefly, in the 1980s. We need to go back. Mystery 99. Uranus rotates on its side. Its axis is tilted 98 degrees. Something knocked it over, probably a massive collision early in solar system history. But what? And did the impact also create Uranus's moons? The details are lost to time. Mystery 100. The final mystery is the simplest and the hardest. Why is there something rather than nothing? Why does the universe exist at all? The Big Bang describes how the universe evolved from a hot, dense state. Inflation explains how it became smooth and large. But what came before? Why did the Big Bang happen? Some theories suggest the universe is cyclic, endlessly expanding and contracting. Others propose the universe arose from quantum fluctuations in a primordial vacuum. Maybe our universe is one bubble in an eternal multiverse. Or maybe the question itself is meaningless. Maybe time began with the Big Bang, and asking what came before is like asking what's north of the North Pole. We don't know, and perhaps we never will, but not knowing is okay. Mysteries aren't failures, they're invitations. Every unanswered question is a door waiting to be opened. Every puzzle drives us forward, pushing us to explore, to observe, to think more deeply. The universe doesn't owe us explanations, but it gives us wonders, and that's enough. We've reached 100 cosmic mysteries. Some will be solved in our lifetimes. Others might take centuries. A few may remain forever beyond our reach. But each one reminds us that the universe is stranger, richer, and more beautiful than we ever imagined. Rest now. Let these mysteries settle into your thoughts like stars settling into their places in the night sky. Sleep gently, knowing that tomorrow the universe will still be here, vast and mysterious and filled with light. You're still here. Good. We've cataloged 100 mysteries, each one a thread in the vast tapestry of cosmic questions. But let me take you deeper now, not into new mysteries, but into what these mysteries mean, what they tell us about ourselves, about our place, about the nature of understanding itself. Because the mysteries aren't just out there in space, they're also in here, in the act of wondering. Think about how far we've come. A few hundred years ago, people didn't know what stars were made of. They didn't know the sun was a star. They thought the Milky Way was a cloud of luminous gas, not a galaxy of hundreds of billions of suns. They had no concept of atoms, of nuclear fusion, of space-time curvature. The universe was smaller then, simpler, more manageable, but also less true. Now we know so much more. We've measured the age of the universe to within a few tens of millions of years. We've detected gravitational waves from black holes colliding billions of light years away. We've landed robots on comets and flown spacecraft past Pluto. We've discovered thousands of planets around other stars. We've traced the cosmic web of dark matter that structures the universe. And yet, the more we learn, the more we realize how much we don't know. Dark matter, dark energy, the origin of cosmic inflation, the nature of consciousness, the fate of information in black holes. Each answer breeds new questions. The frontier doesn't shrink, it expands. Does that frustrate you, or does it excite you? Both responses are valid. There's a certain comfort in knowing, in understanding, in having a complete picture, but there's also beauty and mystery, in the unknown, in the edges of the map where the cartographers wrote, "Here be dragons." Those edges are where discovery happens, where curiosity lives. Let's talk about curiosity for a moment. What drives it? Why do we care about things that don't affect our daily lives? Whether dark matter is made of WIMPs or axions doesn't change the taste of your coffee. The expansion rate of the universe doesn't impact your commute. Fast radio bursts won't pay your bills. And yet, we wonder. We build telescopes. We write equations. We stay up late thinking about neutron stars and exoplanets and the cosmic microwave background. Why? Maybe it's because we're pattern-seeking creatures. Our brains evolved to find patterns, to predict, to understand. When we see something that doesn't fit the pattern, something unexpected or unexplained, it bothers us. We want to resolve the dissonance. We want things to make sense. Or maybe it's deeper than that. Maybe curiosity is a kind of longing, a desire to connect with something larger than ourselves. The universe is vast and we are small. But through understanding, through science, through observation and thought, we touch that vastness. We make it ours. Consider the cosmic microwave background, light that's been traveling for 13.8 billion years. When you look at a map of the CMB, you're seeing the universe as it was 379,000 years after the Big Bang. You're looking back in time. You're witnessing the birth of structure, the seeds of galaxies, the echoes of creation. That light passed through voids and filaments, through the dark ages before stars formed, through the reionization epoch, through billions of years of cosmic expansion. And now it's here, captured by our instruments, analyzed by our computers, contemplated by our minds. We're connected to that ancient light. We're part of the same story. Or think about the atoms in your body. The hydrogen in your cells was forged in the Big Bang. The carbon, nitrogen, and oxygen were created in the cores of massive stars and scattered when those stars exploded. The iron in your blood came from supernovae. The gold in a ring on your finger might have come from a neutron star merger. You are literally made of stardust. Not metaphorically, literally. Every atom in your body except hydrogen has been through a star. You're a collection of atoms that formed billions of years ago, in different places, in different events. And somehow, those atoms found their way to Earth, to your parents, to you. You're a temporary arrangement of cosmic material. When you die, those atoms will scatter again. They'll become soil, water, air. Some will be taken up by plants, by animals, by other people. Your atoms are immortal, even if you aren't. Does that thought comfort you, or does it make you feel insignificant? Again, both are valid. You are insignificant in one sense. The universe is enormous. Earth is tiny. Your life is brief. In cosmic terms, you're a flicker, a single frame in a film that runs for trillions of years. But you're also significant. You're a structure capable of understanding. You're matter that has become aware of itself. The universe, through you, contemplates its own existence. That's remarkable. That's rare, as far as we know. Maybe even unique. We've talked about the Fermi paradox. Where are the aliens? If the universe is so vast and planets so common, why haven't we seen anyone else? There are many possible answers. Maybe civilizations destroy themselves. Maybe interstellar travel is too hard. Maybe we're looking in the wrong way or at the wrong time. Or maybe, just maybe, life is rare. Maybe intelligent life is rarer still. Maybe Earth is special. Not because we're at the center of the universe, we're not. But because we're one of the few places, possibly the only place in our cosmic neighborhood, where consciousness has emerged. If that's true, if we're alone, then what we do matters enormously. We're the universe's way of knowing itself. We're the only witnesses, the only storytellers. But even if we're not alone, even if there are millions of civilizations out there, we're still special. Because each civilization is unique. Each one tells a different story. Each one explores the universe in its own way. And we're part of that. We're Earth's contribution to the cosmic conversation. We're the ones who built telescopes and spacecraft, who wrote equations and painted pictures, who asked questions and sought answers. That's our role. That's our gift. Now, let's talk about time. The universe is 13.8 billion years old. Humans have been around for a few 100,000 years. Civilization for maybe 10,000. Science for a few hundred. Spaceflight for about 70. We're so new, so young. And yet, we've already achieved so much. We've gone from thinking the Earth was flat to landing robots on Mars. From thinking atoms were indivisible to splitting them. From thinking the Milky Way was the entire universe to discovering trillions of galaxies. Imagine what we might know in another 100 years. another 1,000, another million. If we survive. That's the caveat. Civilizations are fragile. We face challenges, climate change, nuclear weapons, pandemics, artificial intelligence. We could destroy ourselves. It's happened before on smaller scales. Civilizations have collapsed. Empires have fallen. Knowledge has been lost. And if we fail, if we don't make it, the universe will continue without us. Stars will keep burning. Galaxies will keep colliding. The expansion will keep accelerating. None of it depends on us. We're observers, not controllers. We matter to ourselves, but the cosmos doesn't need us. But maybe we'll make it. Maybe we'll solve our problems. Maybe we'll spread to other worlds, other stars. Maybe we'll build habitats in space, terraform planets, send ships to distant galaxies. Maybe our descendants will be as different from us as we are from single-celled organisms. Maybe they'll merge with machines, or upload their minds, or evolve into something we can't imagine. Maybe they'll solve the mysteries we've talked about. Dark matter, dark energy, quantum gravity, the origin of the universe, the nature of consciousness. Maybe they'll discover new mysteries, questions we haven't even thought to ask. The future is open, it's unwritten, and that's both terrifying and beautiful. For now, we're here, on this small planet, orbiting this ordinary star, in this quiet corner of the galaxy. We're listening to fast radio bursts and watching for gravitational waves. We're building rovers and telescopes and particle colliders. We're asking questions and sharing what we learn. We're dreaming of what might be out there, beyond the horizon, beyond the reach of our instruments, beyond the limits of our imagination. And that's enough. That's our purpose, if we have one. To wonder, to explore, to understand as much as we can, for as long as we can. Let your mind rest now. Drift among the thoughts we've shared. You're part of this story. You're a consciousness in a cosmos full of mysteries. You're stardust, asking questions about stars. Sleep gently, knowing that the universe is vast and strange and filled with beauty. When you wake, it will still be here waiting. We've journeyed far together, through 100 mysteries, through reflections on meaning and scale. Now let's turn to something quieter. The tools we use, the methods of discovery. Because understanding the cosmos requires more than curiosity. It requires instruments, mathematics, collaboration. Let me walk you through how we know what we know. Start with light. Almost everything we know about the universe comes from light. Visible light, yes, but also infrared, ultraviolet, X-rays, gamma rays, radio waves. All electromagnetic radiation, traveling at the speed of light, carrying information from distant places and distant times. When you look at a star, you're not seeing it as it is now. You're seeing it as it was when the light left. The farther away the star, the farther back in time you see. The nearest star, Proxima Centauri, is 4.2 light-years away. We see it as it was 4 years ago. The Andromeda Galaxy is 2.5 million light-years away. The light we see left before humans existed. The cosmic microwave background shows us the universe as it was 13.8 billion years ago. We're time travelers, in a sense, looking backward through the history of light. But light can be deceptive. Space isn't empty. It's filled with dust, gas, plasma. Light gets absorbed, scattered, redshifted. To see clearly, we need different wavelengths. Radio waves pass through dust clouds that block visible light. Infrared reveals cool objects like brown dwarfs and forming planets. X-rays show hot gas around black holes and neutron stars. Gamma rays trace the most violent events, supernova explosions and gamma ray bursts. Each wavelength tells a different story. Each adds a piece to the puzzle. And we don't just look with light anymore. We listen with gravitational waves. LIGO and Virgo detect ripples in space-time, caused by colliding black holes and neutron stars. These events are invisible in light, or nearly so. But gravitational waves pass through matter unimpeded. They carry information from the heart of the collision, from regions no photon can escape. When we detected the first gravitational wave signal in 2015, It opened a new window, a new sense. We'd been deaf to the universe's low rumble. Now we can hear it. We also detect neutrinos, ghostly particles that barely interact with matter. Trillions of neutrinos pass through your body every second, most from the sun. They pass through the Earth without slowing down. Special detectors, buried deep underground or submerged in Antarctic ice, catch a few. When a supernova explodes, it releases a burst of neutrinos. We detected neutrinos from supernova 1987A, a star that exploded in the Large Magellanic Cloud. The neutrinos arrived hours before the light because they escaped from the core immediately, while the light took time to fight its way through the star's outer layers. Neutrinos give us a direct view of the core, the engine of the explosion. And then there's cosmic rays, high-energy particles, mostly protons, raining down from space. They hit the atmosphere and create showers of secondary particles. By studying these showers, we infer the energy and direction of the original cosmic ray. The most energetic cosmic rays have energies 100 million times higher than anything we can produce in particle colliders. Where do they come from? We're still figuring it out. But instruments are only part of the story. We also need mathematics. Physics is written in the language of equations. Einstein's field equations describe how mass and energy curve space-time. The Schrödinger equation describes how quantum systems evolve. Maxwell's equations govern electromagnetism. These equations aren't just descriptions. They're predictive tools. They tell us what should happen in situations we've never tested. And when we test them, they're almost always right. General relativity predicted gravitational waves a century before we detected them. It predicted black holes decades before we found evidence for them. It predicted the bending of light by gravity, which was confirmed during a solar eclipse in 1919. Quantum mechanics predicted the existence of antimatter, which was discovered shortly after. It predicted the energy levels of atoms with astonishing precision. The equations work. They describe reality. But why? Why is the universe mathematical? Why does it follow rules we can write down? That's another mystery, deeper than the ones we've listed. Maybe the universe isn't mathematical. Maybe math is just the language we use to describe patterns we see. Or maybe there's something fundamental about mathematical structure, something that connects thought and reality in ways we don't fully grasp. Let's talk about collaboration. Science isn't done by lone geniuses anymore. It's done by teams, often thousands of people spread across dozens of countries. The Event Horizon Telescope, which imaged the black hole in M87, involved over 200 scientists. The detection of gravitational waves required decades of work by hundreds of researchers, building detectors, analyzing data, refining techniques. The Large Hadron Collider employs thousands of physicists and engineers. No one person could build these instruments or analyze the data alone. Science is collective. It's cumulative. Each generation builds on the work of the previous one, and science is self-correcting. When a result doesn't replicate, when an observation contradicts predictions, we don't ignore it. We investigate. Sometimes the anomaly leads to new discoveries. The orbit of Mercury didn't match Newton's predictions. That anomaly led Einstein to general relativity. The rotation curves of galaxies didn't match what visible matter predicted. That anomaly led to dark matter. Other times, anomalies are errors, faulty instruments, incorrect analysis. But either way, science adapts. It adjusts. It gets closer to truth, step by step. This doesn't mean science has all the answers. It doesn't. We've spent hours talking about mysteries. But science is the best tool we have for finding answers. It's a process. Observe, hypothesize, test, refine, repeat. It's slow, it's painstaking, but it works. And it's given us an understanding of the universe that ancient philosophers couldn't have dreamed of. Consider the scale of what we've achieved. We've measured the distance to galaxies billions of light years away. We've calculated the mass of black holes millions of times heavier than the sun. We've determined the age of the universe to within a fraction of a percent. We've mapped the cosmic web of dark matter. We've detected planets around other stars and characterized their atmospheres. We've found water on Mars and organic molecules on comets. We've listened to gravitational waves and decoded the cosmic microwave background. All of this done by curious minds with instruments and equations. All of this in a few short centuries. It's astonishing, and we're not done. New telescopes are coming online. The James Webb Space Telescope is already sending back images of unprecedented detail. The Vera Rubin Observatory will survey the entire southern sky every few nights, detecting transient events and mapping the distribution of galaxies. The Square-Kilometer Array will be the most sensitive radio telescope ever built, probing the early universe and searching for faint signals. The next generation of gravitational wave detectors will hear black hole mergers from across the cosmos. We're building neutrino telescopes in the ice and in the ocean. We're planning missions to Europa and Enceladus to search for life in subsurface oceans. We're designing spacecraft to visit interstellar objects if another one passes through. Every new instrument is a new set of eyes, a new way of seeing, and each one reveals surprises. We thought the universe was simple. It's not. We thought the Milky Way was the whole cosmos. It's not. We thought planets were rare. They're not. We thought the expansion was slowing. It's not. Every assumption has been challenged. Every expectation has been exceeded. The universe is stranger than we thought, and probably stranger than we can think. But that's okay. That's the adventure. We don't need all the answers. We just need the willingness to ask questions, to look, to wonder. The tools we use, the telescopes and detectors and equations, they're not just instruments. They're extensions of our senses and our minds. They let us see farther, hear deeper, understand more. They connect us to the cosmos in ways our ancestors couldn't imagine. When we point a telescope at a distant galaxy and see its light that's been traveling for millions of years, we're touching that galaxy. We're making contact. We're part of the same reality. Rest now. Let the instruments and equations fade into the background. You don't need to understand the math. You don't need to build a telescope. You just need to appreciate what they reveal. The universe is vast and intricate and beautiful. And we're learning to see it, piece by piece, mystery by mystery. Sleep softly, knowing that somewhere, a telescope is watching the sky. Somewhere, a detector is listening for gravitational waves. Somewhere, scientists are analyzing data, asking questions, seeking answers. The work continues, even while you rest. Let's talk about the future now. Not the distant future, not billions of years from now, but the near future, the next few decades. What might we discover? What mysteries might we solve? What new questions might arise? The universe doesn't stand still, and neither does our understanding of it. Let me walk you through what's coming. First, exoplanets. In the next 10 years, the James Webb Space Telescope and other instruments will study the atmospheres of dozens of potentially habitable worlds. We'll look for biosignatures, chemical traces that could indicate life. Oxygen, methane, phosphine, ozone. If we find them in the right combinations, it could be the first evidence of life beyond Earth. Not proof, but a strong hint, a tantalizing possibility. And if we find nothing, that's interesting too. It tells us life might be rarer than we hoped, or harder to detect, or different from what we expect. We're also planning missions to the outer solar system. Europa Clipper will orbit Jupiter and study Europa's subsurface ocean. It will measure the ice shell's thickness, search for plumes, and analyze the surface chemistry. If it finds organic molecules, if it detects signs of hydrothermal activity, it will strengthen the case for life. A follow-up mission might land on Europa, drill through the ice, and explore the ocean directly. But that's decades away. For now, we'll orbit and observe. Dragonfly, a mission to Titan. We'll send a drone to fly through Titan's thick atmosphere and land on its surface. It will study the chemistry of the methane lakes, the organic compounds raining from the sky, the potential for life in a completely alien environment. Titan is like a frozen version of early Earth, before life began. Understanding Titan might help us understand how life started here, and if we're very lucky, we might find life there too. Life unlike anything on Earth. Life in liquid methane instead of water. Life based on different chemistry, different energy sources. It's a long shot, but it's possible. Mars is also a target. Perseverance rover is currently collecting samples, drilling into rocks and storing them in sealed tubes. A future mission will retrieve those samples and bring them back to Earth. When we analyze them in laboratories here, we'll be able to study Martian geology with unprecedented detail. We'll look for signs of ancient life, microbial fossils preserved in the rock. We'll measure isotopes, trace elements, organic molecules. If Mars once had life, the evidence might be in those samples. And if it still has life, deep underground in aquifers or ice pockets, we might find genetic material, cells, something unmistakable. Gravitational wave astronomy will expand. LIGO and Virgo are being upgraded. New detectors are being built in Japan and India. Together, they'll detect hundreds of black hole and neutron star mergers every year. We'll map the population of black holes, measure their masses and spins, test general relativity in extreme conditions. And we'll listen for signals we haven't predicted. Unexpected events, maybe collisions between exotic objects, primordial black holes or boson stars. Maybe signals from the early universe, from cosmic strings or phase transitions. Gravitational wave astronomy is still in its infancy. The best discoveries might be things we haven't imagined yet. The Vera Rubin Observatory will revolutionize time-domain astronomy. It will survey the sky every few nights, detecting anything that changes or moves. Supernovae, asteroids, variable stars, flaring black holes, fast radio bursts, kilonova explosions from neutron star mergers. It will generate enormous amounts of data, terabytes every night. Machine learning algorithms will sift through it, flagging interesting events for follow-up. And the data will be public. Anyone, anywhere, can access it. Citizen scientists, students, hobbyists. Astronomy will become more democratic, more collaborative. We'll also probe dark matter more directly. Dozens of experiments around the world are searching for dark matter particles. They use different techniques. Some look for direct collisions between dark matter and atomic nuclei. Others search for dark matter annihilation or decay, which would produce gamma rays or other particles. So far, nothing. But the experiments are getting more sensitive. If dark matter is made of WIMPs, we should find them soon. And if we don't, that's informative too. It means dark matter is either much heavier or much lighter than WIMPs. Or it interacts even more weakly, or it's something else entirely. Each null result narrows the possibilities. Dark energy is harder to study, but upcoming surveys will measure the expansion history of the universe more precisely. They'll map millions of galaxies, trace baryon acoustic oscillations, measure gravitational lensing. They'll determine whether dark energy is constant or changing. If it's changing, that tells us it's not a cosmological constant. It's something dynamic, something we need to understand. And that might point us toward new physics, new fields, new forces. Quantum computing might help too. Simulating quantum systems on classical computers is hard. Quantum computers could simulate them directly, giving us insights into quantum gravity, black hole interiors, the early universe. We're still in the early stages. Current quantum computers are small and noisy, but they're improving. In a decade or two, they might be powerful enough to tackle problems we can't solve any other way. Artificial intelligence is already transforming astronomy. Machine learning algorithms classify galaxies, detect exoplanets, find gravitational lenses. They sift through data faster and more thoroughly than humans can. But they're tools, not replacements. They find patterns. Humans interpret them. The combination is powerful. And as AI improves, as algorithms become more sophisticated, they'll help us find things we'd miss otherwise. Subtle correlations, faint signals, hidden structures. And then there's the search for extraterrestrial intelligence. SETI, the search for extraterrestrial intelligence, has been listening for radio signals for decades. Nothing yet, but the search is expanding. New telescopes, new wavelengths. Optical SETI looks for laser pulses. Some researchers search for technosignatures, signs of advanced technology, megastructures like Dyson spheres, industrial pollution in exoplanet atmospheres, artificial lights on the night side of planets. These searches are speculative, but they're worth doing. If we find something, anything, it would be the most profound discovery in human history. And if we don't, we'll keep looking. Because the question is too important to ignore. But let's be realistic. Most of these mysteries won't be solved quickly. Dark matter and dark energy have resisted explanation for decades. The Fermi paradox might never be resolved unless we find aliens or conclusively prove we're alone, and neither seems imminent. The origin of the universe, the nature of consciousness, the fate of information in black holes, these are deep questions. They might take centuries to answer. Some might be unanswerable, but that's okay. The journey matters more than the destination. The process of discovery, the slow accumulation of knowledge, the gradual refinement of understanding. That's what science is. And as we learn more, we'll find new mysteries, new questions we couldn't ask before, new puzzles hidden in the data. The frontier expands. It always has. It always will. There's no end to discovery, no point where we'll know everything. The universe is too vast, too complex, too strange. And that's beautiful. It means there's always more to explore, always more to wonder about. For now, rest. Let the future unfold in its own time. You don't need to solve these mysteries. You just need to appreciate them, to know they exist, to let them inspire you. Sleep gently, knowing that the search continues, that somewhere someone is looking at the stars, asking questions, seeking answers, and maybe, just maybe, they'll find something extraordinary. We're nearing the end now. Let me bring this journey to a close gently by stepping back and reflecting on what we've covered. 100 cosmic mysteries, reflections on meaning, on scale, on the tools of discovery, on the future. It's been a long road, and you've walked it with me. Thank you for that. Let's think about what mysteries do to us, how they shape us, because understanding the universe changes who we are. It changes how we see ourselves, our world, our place. Before Copernicus, people thought Earth was the center of everything. The sun, moon, and stars revolved around us. We were special, central, unique. Then Copernicus showed that Earth orbits the sun. We were displaced, no longer the center. Galileo's telescope revealed moons orbiting Jupiter, proving not everything circles Earth. The universe didn't revolve around us. We were part of a larger system. Then we discovered the Milky Way is a galaxy, one of many. Hubble showed the universe is expanding, full of countless galaxies receding into the distance. We shrank again, not just displaced from the center, but revealed as inhabitants of an ordinary planet, orbiting an ordinary star, in an ordinary galaxy, in an ordinary part of the universe. There's nothing special about our location. The Copernican principle. We're not privileged observers. The universe looks roughly the same from anywhere. But then we discovered we're made of atoms forged in stars. We learned that the heavy elements in our bodies came from supernova explosions. We're connected to the cosmos. We're not separate from it. We're part of it, literally. The universe isn't something out there. It's here, in us. We're the universe observing itself. That's special in a different way. Not because of where we are, but because of what we are. And we might be rare. The Fermi paradox suggests intelligence might be uncommon. Maybe we're one of the few places where matter has organized itself into consciousness. If so, that's staggering. It means we matter, not to the universe, which doesn't care, but to ourselves, to the story. We're witnesses, storytellers. We're the ones asking why. Does that responsibility weigh on you, or does it lift you up? Both, maybe. It's heavy to think we might be alone, that the future of consciousness in this region of space depends on us. But it's also empowering. It means what we do matters, how we treat each other, how we care for our planet, how we approach the future. These aren't just practical concerns. They're cosmic ones. Let me share a thought experiment. Imagine you're standing outside on a clear night. You look up at the stars. You see thousands of them, tiny points of light scattered across the sky. Each one is a sun, many with planets. Some of those planets might be habitable, some might harbor life. And you, standing there, are made of the same atoms as those stars. You're stardust, contemplating stardust. For a moment, the boundary between you and the universe blurs. You're not separate, you're continuous. The atoms in your hand were once in a star. The oxygen you breathe was exhaled by ancient bacteria. The carbon in your cells cycled through countless organisms before you. You're part of a chain, a flow, a process that's been running for billions of years. And you'll continue. Your atoms will outlive you. They'll become part of something else. A tree, a river, a cloud, another person. The atoms are immortal. Only the pattern changes. Does that make you feel small or vast? I think it's both. You're tiny in space and time. A brief flicker, but you're also connected to everything. You're part of the whole. Now think about the mysteries we've discussed. Fast radio bursts, dark matter, black holes. Each one is a reminder that the universe is bigger and stranger than we thought. Each one challenges our assumptions, and that's good. It keeps us humble. It reminds us we don't have all the answers. We're learning, we're exploring, we're growing. But mysteries also inspire us. They drive us to build better telescopes, to write new equations, to send spacecraft to distant worlds. They push us forward. Without mystery, without questions, science would stagnate. We'd stop looking. We'd stop wondering. The universe would become static, known, finished. But it's not finished. It's alive with possibility. And it's not just scientists who benefit. Everyone does. Understanding the cosmos enriches us. It gives us perspective. When you're stressed about something small, something trivial, it helps to remember you're on a planet orbiting a star in a galaxy with hundreds of billions of other stars. Your problems are real. They matter to you. But they're also tiny in the grand scheme. The universe doesn't care if you missed a deadline or had an argument. It just keeps expanding. Stars keep burning. Galaxies keep colliding. There's something comforting in that. A kind of freedom. Your worries are temporary. The cosmos is eternal. But don't let that make you nihilistic. Just because the universe is vast doesn't mean your life is meaningless. Meaning isn't given by the universe. It's created by you, by us, by what we do, how we live, who we love. The universe doesn't need us to have meaning. We give ourselves meaning, and that's powerful. Let me tell you a story. In 1990, Voyager 1, which had already passed Neptune and was leaving the solar system, turned its camera back toward Earth. From 6 billion kilometers away, it took a photo. In that image, Earth appears as a tiny pale blue dot, less than a pixel wide, suspended in a beam of sunlight. Carl Sagan, the astronomer who suggested the photo, wrote about it. He said every human who ever lived on that dot. Every triumph and tragedy, every war and peace, every love and loss, all of it on that tiny stage. And he urged us to be kind to each other, to cherish this fragile world, because it's the only home we have. That image, that pale blue dot, is a kind of mirror. It shows us how we look from outside, small, fragile, alone in the dark. But it also shows us something else, that we're together, that we share this world, that despite our differences, we're all human, all made of the same atoms, all passengers on the same planet. The cosmic perspective doesn't diminish us, it connects us. And maybe that's the real lesson of cosmic mysteries. Not just that the universe is big and we're small, but that we're part of something vast and beautiful, that we're connected to the stars and to each other. That curiosity, wonder, and the search for understanding are worth pursuing, not because they'll solve all our problems, but because they remind us of what's possible. They remind us to look up, to ask questions, to dream. So as you drift toward sleep now, carry that with you. You're a small part of a vast cosmos, but you're also a conscious part. A part that can wonder and understand. A part that can look at the night sky and ask why, and that's enough. That's more than enough. Sleep well, traveler. Rest among the stars. This is the end. The final part. We've journeyed through 100 mysteries, through reflections on scale and meaning, through tools and futures and perspectives. Now, let me bring everything together, gently, like threads weaving into a final tapestry. The universe is a place of contradictions. It's vast and empty, yet full of structure. It's ancient and evolving. It's governed by laws we can write down, yet filled with phenomena we don't understand. It's indifferent to us, yet it created us. These contradictions don't need to be resolved. They just need to be held, appreciated, wondered at. Think about light. Light is both a wave and a particle. It travels at a fixed speed, the fastest speed possible. Nothing with mass can reach it. But light, which has no mass, always travels at that speed. It can't go slower. And from light's perspective, if photons could have perspectives, time doesn't pass. A photon emitted from a distant quasar billions of years ago experiences no time between emission and absorption. From its point of view, the journey is instantaneous. But from our point of view, it took billions of years. Time is relative. It depends on your frame of reference. There's no absolute now, no universal present. The universe doesn't have a single timeline. It has countless overlapping ones. This is strange, but it's true. We've tested it. Time dilation is real. Clocks on satellites run faster than clocks on Earth because they're in a weaker gravitational field. GPS systems have to account for this, or they'd give wrong positions. Astronauts on the space station age slightly slower than people on the ground because they're moving fast. The difference is tiny, fractions of a second over a lifetime. But it's measurable. Time is flexible. Space-time is curved. These aren't metaphors, they're descriptions of reality. And yet, despite the strangeness, the universe is comprehensible. We can understand it. Maybe not completely, maybe not yet, but we're making progress. Equations describe the motion of galaxies, the fusion of atoms, the evaporation of black holes. Mathematics, a product of human minds, maps onto the structure of reality. Why? We don't know, but it works. And that's a kind of miracle. Let's talk about beauty. The universe is beautiful, not because it was designed to be, not because anyone made it pretty for us, but because it follows patterns, symmetries, rhythms that resonate with something deep in us. The spiral of a galaxy echoes the spiral of a seashell. The fractal branching of a river delta mirrors the branching of blood vessels in trees. The laws of physics have an elegance, a simplicity that feels almost musical. E equals mc squared. Force equals mass times acceleration. The inverse square law of gravity. These aren't just true. They're beautiful. And the phenomena themselves. The aurora shimmering in polar skies. The rings of Saturn. The nebulae where stars are born, glowing clouds of gas lit from within. The cosmic web, filaments of dark matter stretching across the universe. The afterglow of the Big Bang, a faint microwave hum filling all of space. These are beautiful. They inspire awe. They make us feel something beyond words. Maybe that's why we explore. Not just to understand, but to experience, to witness, to stand in the presence of something greater than ourselves and let it fill us with wonder. Science gives us the tools to understand, but the wonder comes from something deeper, from the part of us that looks at the night sky and feels small and connected and curious all at once. Now, what do you do with all this? With 100 cosmic mysteries and hours of reflection? You don't need to memorize them. You don't need to become an astronomer. You just need to let them settle into you, to let them change how you see the world, even slightly. Maybe the next time you look at the stars, you'll remember that some of them are dead, their light still traveling toward us. Maybe you'll think about dark matter, invisible scaffolding holding galaxies together. Maybe you'll wonder about fast radio bursts flashing across the cosmos, each one a mystery we're only beginning to unravel. Or maybe you'll just feel wonder, and that's enough. Wonder doesn't require understanding. It just requires openness, a willingness to be amazed, to let the universe surprise you. We started this journey with a simple promise: 100 cosmic mysteries. We've covered them. Oumuamua, the interstellar visitor, the wow signal, never repeated, fast radio bursts from distant galaxies, dark matter, the invisible glue, dark energy, pushing space apart, black holes where physics breaks, neutron stars, cities of pure neutrons, gravitational waves, ripples in space-time, Tabby's star, dimming erratically, odd radio circles, structures we don't understand, the cosmic microwave background, light from the Big Bang, the Hubble tension, expansion rates that don't agree, the baryon asymmetry, more matter than antimatter, the Fermi paradox, where are the aliens, quantum entanglement, spooky action, the measurement problem, collapsing wave functions, the cosmological constant problem, vacuum energy too large, the black hole information paradox, information lost or preserved, exoplanets in every configuration, subsurface oceans on icy moons, methane lakes on Titan, phosphine in Venus's clouds, methane spikes on Mars, Saturn's rings, younger than expected, Uranus knocked on its side, the Oort cloud, unseen, Planet 9, hypothetical, the pale blue dot, Earth from afar, and 50 more, pulsars, quasars, magnetars, brown dwarfs, supernovae, gamma-ray bursts, cosmic rays, the great attractor, the cosmic web, rogue planets, white dwarfs, strange matter, superionic ice, the moon's magnetic patches, Iapetus's ridge, Hyperion static, the axis of evil, inflation, quintessence, the big rip, the big crunch, the multiverse, Hawking radiation, the GZK cutoff, supersymmetry, string theory, quantum gravity. Each one a question, each one a door. And here's the thing, you don't need to solve them. The mysteries aren't problems to fix. They're invitations to think, to learn, to explore. They remind us the universe is bigger than we are, stranger, more beautiful, and they connect us. Every human who's ever looked up at the stars has felt the same wonder, the same curiosity, the same smallness and vastness combined. We're part of a long tradition, astronomers and philosophers, poets and dreamers, all of us looking up, asking why. So as this journey ends, as you drift into sleep, carry this with you. You're made of stardust. You're a consciousness in a cosmos full of mysteries. You're part of a story that began 13.8 billion years ago and will continue for trillions more. Your life is brief, but it's also miraculous. You exist, you wonder, you're here now in this moment, aware of the universe and your place in it. That's enough. That's everything. Sleep now. Let the mysteries fade into the background, like stars fading at dawn. You don't need to hold on to them. They'll be here when you wake. The universe isn't going anywhere. It will still be vast and strange and full of light, and you'll still be part of it. A small part, yes, but a part nonetheless. Rest gently, traveler. Dream softly, and when you wake, look up. The stars are waiting. If one of these mysteries stayed with you, let me know which one. If something surprised you, inspired you, or made you think differently, I'd love to hear. That's what these mysteries are for. Not just to inform, but to transform, to open doors in your mind, to let the cosmos in. Good night. Sleep well. And thank you for wandering through the dark with me.